First question that I have on my left is the heating of limestone produces. So the statement makes you understand that when you heat limestone, what product do you get? You have ammonia there, and ammonia is no way connected to limestone. Milk of magnesia, also nowhere near. That is magnesium hydroxide. Then you have potassium hydroxide. So when you look at the ammonia, milk of magnesia, and potassium hydroxide, they are all bases. So one thing to know, they are all bases. But when you heat limestone, what the product that you get is calcium oxide. That is CaO, capital C, small a O. That is the chemical formula for calcium oxide. Then number two, is that malic acid is found in. Then you had a palm oil, citrus fruits, apple, and vinegar. But you should understand that palm oil, the acid found there is a palmitic acid. Then citrus fruits, it's either you have this ascorbic acid. You're welcome. Okay, so looking at the malic acid found in, it cannot be found in palm oil because palm oil gives you palmitic acid. Then citrus fruit gives you ascorbic acid. Then the vinegar gives you acetic acid. So the best answer or possible answer for malic acid is apple. Apple. I remember giving you the source of acid and the acid and their sources. Okay. The next one, you have all these are examples of organic acids except metanoic acid is an organic acid, malic acid, and butanoic acid. They are all organic acids, with the exception of hydrochloric acid, that's inorganic acid. You have acetic acid. Hey, sorry, ethanol, ethanol. They are all inorganic acids. So you have metanoic, butanoic, and malic acid as organic, um, having organic products. Okay, then number 8, you were asked who defined proton basis as a proton acceptor. Then the correct answer is supposed to be brancellary acid. Lewis defined the base as an electron pair donor. Arrhenius defined a base as um, a substance that accepts hydroxide ions in solution. The Newton, it's not false, so the Newton doesn't even come in play here. Number 10, if you have any question to what I've been I'm talking about, you can unmute yourself and ask questions to what we are talking about. Okay. The next one, you ask the salt form when insufficient acid is present to neutralize a given base or alkaline is called. Then the double salt deals with two salts having having the same oxidation state. So the double salt deals with varying between two salts. Then acidic salt is when part of the replaceable hydrogen ions are replaced by metal. Then with the normal salt, all replaceable ions are replaced by a metal cation. But the basic salts are formed when insufficient acid is present to neutralize a given base or alkaline. Okay, then you will ask the lower part of the seed's plumum is referred to as the lower part of the seed's plumum is referred to as, then the correct answer is hypocotyl. Hypocotyl. The epicotyl is the upper part of the plumum. The cotyledon is the seed leaf, the leaves of a seed. Then epigeal stalk. So you can have it as the stalk of the epigeal. Okay. The handle, let me put it that way. Number 7, he said oxides with both acidic and basic properties are referred to as. The answer is amphoteric oxides. That is, they act as both, they can react with both a base and an acid. They react with both bases and acids. And in a way, they can act as an acid, they can act um, as a when reacting an acid and a base, they can react with both at the same time. They are not neutral, uh, they're not neutral entities, but they can react with both at the same time. Okay. Then your first question was the elongation of the dash causes the cotyledon to remain in the ground during hypogeal germination. If you could remember, we define hypogeal germination as the type of germination where the cotyledon is seen below the ground. And I further explained that it happens as a result of the elongation of the epicotyl. Results as the elongation of the epicotyl. Then when you deal with the epigeal germination, it deals with the elongation of the hypocotyl. Okay, so the last two. Which of the following is not a physical property of hydrogen? They are all properties of the last three is they are all properties of hydrogen. And if you could remember, hydrogen does not support burning. Hydrogen does not support burning. So hydrogen, the possible answer A, that it supports combustion. No, it's an odorless gas. It is not soluble in water. It's a reducing agent. So it does not support burning. So your answer there does not support our question. Then question number 2. The following are internal conditions that aid in germination of seeds, except enzymes are it's an internal factor. Um, Energy stored from food, also an internal factor. Light in seeds also forms an internal factor. So chlorophyll, even uh, chlorophyll does not, it's not even a factor that aids germination. Chlorophyll is not even a factor that aids germination. Okay, so that was just a way to revise what you were I taught you over the weeks. Today, you can go through them. They are easy to understand. I try hard to simplify it in a way that even when you are reading them, you understand what it means. Okay, thank you. Okay, so we will continue from where we stopped the last time. We looked at acids. After we had finished the acids, we looked at what base and everything about the base. Then we look at salt and how the how salts are being produced and how salts form, how you can identify salt. Now, there are certain ways that you can identify all these three substances. So, by means of pH of solution, you can identify whether this substance is an acid, this substance is a base, or this substance is a salt. So, the means by which you can be able to identify that this is an acid by way of using if it's an instrument or if it's even a solution that you use to test and know whether this is an acid, a base, or a salt, we use what we call the pH. pH. Now, pH is defined as a measure of its acidity or alkalinity. So it's an acid or a base. So it measures the amount of acid or a base in a solution. Now, there's no neutral here because neutral is neutral. Now remember, neutral is not, it's not zero. Neutral doesn't mean zero. So this pH, it deals with the measure of how acidic a substance is or how alkaline a substance is. Now pH is also is an abbreviation for power, potential hydrogen, hydrogen potence, that is, or power of hydrogen. These are all ways that you can identify. Sorry, someone seems to be sending messages. So okay, so pH can also be defined as a measure of the concentration of hydrogen ions in solution. What I just said, that how the power of hydrogen is assessed is a measure of the concentration of hydrogen ions in solution. So pH measures the concentration of hydrogen ions in solution. Now, mathematically, or with pure chemistry students, you can define pH as the negative logarithm of hydrogen ion concentration of a solution. It can be defined as the negative log or negative logarithm of the hydrogen ions concentration of a solution. So that is pH. I don't know whether uh, I should have written it mathematically for you. It seems it skipped me a bit. But pH can be defined as the measure of its acidity or alkalinity, one. It can also be defined as the measure of the concentration of hydrogen ions in a solution. Then three is the negative logarithm of hydrogen ions concentration of a solution. So these three definitions are all acceptable. So you can choose one, and when you are asked what is pH, then you can define pH. Now, in measuring how acidic, how alkaline, how neutral a solution is, the instrument that we use or a system that we apply is a pH scale. pH scale, using the pH meter. We use the pH meter on which there's a scale, so pH scale. So the scale is on the meter. Now, this is the pH scale, the pH meter showing you the scale. Now, this scale runs from 1 to 14. The scale runs from 1 to 14. Now, at the point 7, 7 being the midpoint of from 1 to 14 is the neutral point. Then from 1 to 6, from 1 to 6.9 measures the acidity or acidic content in the solution. Then from 7.1 to 14 measures the alkaline nature of a solution. Now look at how the arrows are showing. you will notice that from the acidic point, the arrow is going to your left, and the basic point, the arrow is moving to your right. Now this means that from the point neutral, that is the 7, so from 7 going down, it determines how acidic a substance is. So when you have 6, 6 is acidic, but when you go to 2, 2 is more acidic than 6 because it's moving down. So 1 is more acidic than 6 because of how the direction of the arrow is. Now I'm going to your on your right, that is the base part or the alkaline part. Notice that when you are moving from 7 to 14, it determines how strong a base is. So when you start at 8, 8 is a weak base as compared to 13, which is stronger than 8. So down, when you're moving down from 7 to 14, it tells you um, how acidic or how strong an acidic solution is. And when you're moving from 8 to 14, also tells you how strong a base is. So if you can look on the diagram, you notice that you have increasing acidity. So from your right to left, it tells. Then from your left to right, it tells you how there's an increase in alkalinity. Now pH scale is a scale numbers is a scale of numbers, normally ranging from 0 to 14. 0 to 14 because it would start from we usually use the 1 to simplify issue. Now, which expresses the acidity or alkalinity of a solution. Now, a pH scale of 7 indicates that a solution is neutral. So anytime you see pH 7, it means that it's neutral. That is where even the salts fall. They find themselves. Then a pH of less than 7 is acidic. A pH of greater than 7 is alkaline or basic. Then on a pH scale, a pH of 3 is more acidic than a pH of 6, as I said. So a pH of 3 is more acidic than an of 6 because the 6 it's moving down to 1, and 1 is more acidic than 2. 2 is more acidic than 3. 3 is more acidic than 4. 4 is more acidic than 5. Then until you get to 6. So moving down determines how acidic a solution is. Also, the pH of 14 is more alkaline than pH of 9. pH of 14 is more alkaline than pH of 9. So that explains how to use the pH scale on the pH meter. Now let's look at how to measure when using this substances, this instrument. So measuring pH. Now to measure the pH of an acid or an alkaline, that is a base, two instruments are used. Instrument number 1, the pH meter, and instrument number 2, the universal indicator. Now this instrument tells you or gives you and predicts rightly whether a substance is an acid or a base. It gives you a correct prediction. It predicts whether the substance is an acid or the substance is a base. Now, a pH meter is an electronic instrument that measures the pH through electrodes and shows it on a scale. So the moment you place a substance on a pH meter, it will move in the form of electrodes that will display whether the substance is acidic or alkaline. With even that, when it's an acid, it will even tell you or indicate to you whether it's a strong acid or a strong base. So at the point where you put or you place an the you are using the pH meter to test for how acidic something is, and on a pH scale it reads 2 or 1. It means that the solution is a strong acid. But the moment it reaches like 5 and 6, it means that the solution is a weak acid. The same thing applies to the base, where when it reaches 9, 8, 8, 9, it's a weak base. But when it reaches 13, 14, what you're having an increase in what? How alkaline a solution is. Now, the second instrument that is being used is the universal indicator. The universal indicator. So, as the name sounds, universal, that is a mixture of a lot of things that have been put in place to ensure that it indicates whether a substance is an acid, a base, or a salt. Now, this is a mixture of several indicators. The indicators are chosen so that the mixture gives a different color at different pH numbers. A color chart is supplied with several indicators showing the color changes. Now, with regards to this universal indicators, it's able to show you or give you colors with respect to how acidic or how alkaline the substance is. So let's say that you are using a universal indicator alongside a pH meter. It will be able to tell you that, oh, if it's acidic, it's a strong acid. So maybe it recalls number 2. Then that number 2 on a pH meter would give you a corresponding color. So should in case you're not even using the pH meter and using the universal indicator, the color change will tell you, or the color that it would result will tell you whether it's a weak acid, a strong acid, or even maybe if it's an acid, or whether it's a base or it's a neutral entity. Now this is how we combine the pH meter and the universal indicator. This is how they look like. Now look at the middle portion. You have the indicator there. The box there, you have dark red, yellow, orange, yellow. Then the neutral point, that is a 7 point. Then you have green, blue, indigo, violet. So that is how to show you the instrument, how it will record how alkaline or basic or neutral an entity is. So should in case that you apply an acidic solution, when the pH of that solution is around 1 or 2, the color on the indicator will indicate red. The color on the indicator will indicate red, to a dark red, to show you that it's a weak, a very strong acid. It's a strong acid. Now, the moment it gives you a pH of 3, you should know that it will give you a red color on the universal indicator. It reads 4 on the pH. That is, as it reads 4 on the pH, it will give you an orange color on the universal indicator. Then with the neutral point, it will be colorless. When you place maybe a salt in an universal indicator, or you place a neutral solution in a universal indicator, it will give you a colorless substance showing that it's neutral in state. Likewise, that of the base aspect. So when it reads 9 to 10, you know that it falls between, it will give you a blue color, so indicating the presence of a base. So when the indicator reads violet, you should know that it's a strong base. So it will give you a pH of either 13 and 14. When you look up above the universal indicator, you notice that there's a litmus written there. That is the use of a litmus paper. So when you place a litmus paper in an acid, blue litmus paper, it will give you red. There will be a red coloration that results from the reaction, because we remember when we're treating properties of an acid, where we learned that one property of an acid is that when you place a blue litmus paper in an acidic solution, the resultant is a red color. Then when you place a neutral entity, example, a salt in the litmus paper, or you place the litmus paper in a salt solution, it will give you a purple color. When you place the litmus paper in a salt solution, to give you a purple color, indicating that that substance is neutral in state, so it's a salt. Then when you place a red litmus paper or a litmus paper in a base, then you have a blue coloration, indicating that the substance is a base. So this diagram is able to show you how to use 3 instruments at a go. One, how to use the litmus paper to indicate whether it's a base or an acid. Now the litmus paper it just indicates whether this is a base, an acid, or it's neutral. That's all. But the universal indicator in the pH meter tells you how strong and how weak the base or acid is. The indicator in the pH meter tells you how strong and how weak the base is. It even indicates how neutral the substance is. So that is how to use the universal indicator, the pH meter, and the litmus paper. These are all instruments that you can use to measure the acidity, alkalinity, or neutral point of any substance. Now, importance of pH, or importance of measuring pH. How important is it to measure pH? Now, one, it is important to know pH. It is important to know that the final product of soap is neutral. There's a mistake there. The final product of soap is neutral. So likewise, salt also a neutral entity. Sorry. It's supposed to be the final product of salt is neutral, not soap. Explaining that, but I wouldn't be going more in detail because it's. Hello.
Yeah, hello, I can hear you, but I don't know whether something happened. But I can hear you now. I don't know whether the rest can hear you, so you can go on. Hello.
First solution. It deals with reaction of weak acids and weak base. So a salt can be acidic in nature and can be basic in a base in nature, but having this weak component and of an acid or a base, not too strong, because it has been neutralized. It could be at a point where, when it has been neutralized, you have, it's not at equal proportion of acid and the base to neutralize each other. I hope I'm okay, or the one coordinating, asking and answering question at the same time. Okay, so number 2, it indicates whether a soil is acidic or alkaline for plant production. So when you have normally this farmers, those in this I would say high-tech or modern farms, when they want to plant a particular kind of crop, and they know that this kind of crop can survive or can grow best in this kind of soil. That is, either the soil is it likes an alkaline medium, or it likes a neutral medium, or it likes an acidic medium. But most plants grow best. Most crop grow best in an alkaline medium. Most plants they yield best in an alkaline medium. Number three, various drugs are produced or are prepared at a given pH, which must be determined. So with drugs too, for them to know the accurate amount of substance to use, they need a pH of a solution to be able to rightly predict how to mix these substances and chemicals together. So when they are mixing and they want to neutralize solutions, they use a pH to say, oh, maybe this is has a pH of 6. It would neutralize the base of of let's say 9 or 8 because they are all weak in nature. They are all weak in nature. Okay, number 4. They are not usually used in acid-based titration to determine whether a solution is acidic or alkaline. So in the next slide, I'm going to explain the use of this acid-based titration. If you could remember in the previous class, we looked at how this titration is, or what the titration is. So it's just like you are measuring a known amount of an acid to the corresponding known amount of a base in a lab. So normally they use the instrument being employed or being used is the um, the burette pipette conical flux. So they use a burette pipette and the conical flux to do that. Okay, so this is a question to test or jog your memory. So you all have to unmute yourself. Um, I want to see how you'll be able to answer the questions and know. So study this table. You have substance. You have a substance. So the substance column, you have A, B, C to F. Then the corresponding pH is below. So A has a pH of 2.5, B has a pH of 7, C of 12, D of uh, C of 1.5, D 12, E 9.5, and F 4.5. So I want to study the table. The questions are after this slide, so that I'll ask the question, then we'll go back and we'll answer the question and see which how appropriate or how best we can answer, we can manage that. Okay. Which of the solution is most acidic? So anyone to answer the which of them is most acidic? Which of the substances is most acidic? Which of the substances is most acidic? Uh-huh.
C.
D.
Come again.
D.
A. Okay, so come again. Is that A what?
A.
Uh-huh. An answer. Anyone with a different answer? Okay. Now it's not only A. It's not only A that is most okay, okay. You no, I wouldn't accept that answer. Even though it's acidic. It's one of the most acidic, but there's one that champions all of them.
Please say C.
Come again.
C.
C, very well. So C has a pH of 1.5. So going down the scale, you have a scale of 1 to 6.9, showing you how acidic a substance is. So 1 is the highest, then it goes down to 6.9 being the lowest. So the C is most acidic. Then number 2, I said which one is most basic? Which one is most basic? Which substance is most basic? Which substance is most basic? Which substance is most basic? With an alkaline. Which of the solution can react with an alkaline? Which of the solution can react with an alkaline? Which substance or solution will
Hello.
react with an alkaline?
Hello.
Hello. Hello. Hello. Explain it very fast. Now, looking at the solutions, you notice that they have varied um, components showing you acids and bases. There are various components showing you acids and bases. So to help you or to make things easier, the A has a pH of 2.5, showing you that it's an acid. The B shows you or tells you that 7 means that it's neutral. It's a neutral entity. The C 1.5 shows you that it's an acid. The D, that is 12.0, shows you that it's a base. Then the E 9.5, it's greater than 7, so also a base. Then you have F, that is 4.5. 4.5, showing you that it's less than 7, so it's an acid. So those that will react with an alkaline, or they are telling you that which ones will react with an alkaline, is find the acids that will react with an alkaline. So you have A, C, and F. A, C, and F, they are all acids that can react with an alkaline. A, C, and F, showing you that it can react with an alkaline. Okay. Then 4, which solution has no effect on litmus paper? Which solution has no effect on litmus paper? Which solution has no effect on
Hello?
litmus paper? Hello?
Hello?
Hello? I'm listening. Hello?
Says B.
B. Very well. B is neutral because it has a pH of 7. So it has no effect on on what? Litmus paper. The answer is B because it has no effect. It's neutral in nature, so it has no effect on litmus paper. Then number 5, which solution will release ammonia gas from ammonium salt? Which solution will release ammonia gas from ammonium salt? Which solution will release ammonia gas from ammonium salt? Which solution will release ammonia gas from ammonium salt? Which solution will release ammonia? Who is there? Who is answering?
Nobody.
It's because you missed the question word. You didn't look at the question word. That's why. Sorry. Okay, so the answer is D and E because they are bases. So the properties of the base is that a base reacting with ammonium salt will release ammonia gas. And the last one, which of the solution will release carbon dioxide gas from carbonate or bicarbonate? Which of the solution will release carbon dioxide from carbonate or bicarbonate? Which of the following solution will release carbon dioxide from carbonate or bicarbonate? Who is there? Which?
ACF.
Okay, ACF. ACF because acid reacts
Hello,
with carbonate.
sir.
Hello.
Hello, sir.
Hello.
ACF.
Hello, sir.
Hello.
Hello, there's a lady talking. Hello.
Hello, sir.
Yes, I'm listening. I'm listening.
Please, can you repeat your question?
The question is, which of the following solution will release carbon dioxide from carbonates or bicarbonates?
Okay, thank you.
Hello, sir.
Yes.
Please, I'll choose C.
Okay, so the answer is acids react with carbonate or bicarbonate to release carbon dioxide gas. So you look out for the acids in the table below. So you have or the table shown. You have A to be an acid, you have C an acid, and you have F an acid. So these three acids would release carbon dioxide when they react with carbonate or bicarbonate. Okay, so this is just to jog your memory on the properties of an acid, on the pH, and the properties of a base. Likewise, what we did in salt. Okay, now a buffer solution. Buffer solution. Now, it's a solution whose pH does not change significantly upon addition of a small amount of an acid or a base. It's a solution whose pH does not change significantly upon addition of an acid or a small amount of an acid or a base. So the moment you are adding or upon addition of an acid to a solution that is already buffer in nature, the pH wouldn't change. The pH wouldn't change. It can also be defined as a solution that resists a change in pH upon addition of a small amount of acids or base. A solution that resists pH, it resists the change in pH, so it wouldn't change, the pH wouldn't change when you add a small amount of an acid or a base. So as I said, I was explaining earlier, with this buffer solution, it normally deals with weak acids and weak bases. So when you are adding more, because it's already weak and it's not highly concentrated already, that there's no change in the pH value. So when the buffer solution reaches a pH of 6.9, upon addition of more acid or an amount of acid to maybe try and increase the acidity of the pH scale of that acid, it will still be 6.9. It wouldn't change. Now, in other words, the pH of buffer solution is always kept constant So buffer solution, they always have a constant pH. Examples of buffer solution, you have blood. So your blood is a buffer solution, and tomato juice, also a buffer solution. So these solutions, they try and resist any change that will occur in their pH value when you want to add an amount of um, acid or a base. Now the indicators, acid-base indicators, as I already said, there are substances which changes color depending on the pH of a solution which is being placed in. Now indicators have the following uses. One, they are used to determine whether a substance is an acid, a base, or a salt, or neutral. Salt is neutral, so determine whether a substance is an acid, a base, or is neutral in nature. And also it's used to determine the end point in acid-base titration. So the moment they go to the lab and they mix, they use a burette pipette and a conical flask to prepare a solution of an acid and a base. They use the indicator to indicate the pH or the color change of what the solution being found, being observed. Now, there are single indicators that are being used. Example is a litmus paper. You have a methyl orange. Methyl orange is a solution, and the phenolphthalein also a solution. So, litmus paper, methyl orange solution, then the phenolphthalein solution, which can be used to show whether a solution is acidic, alkaline, or neutral in nature. Now, the color change is over a narrow pH range. So the next slide will show you a table to tell you when you place an acid, this indicator in an acid, a base, or a neutral entity, what would be the resultant value or component. So in an event where you place a litmus indicator in a neutral medium to give you a purple color, you place a litmus paper in an acidic medium to give you a red color. You place the litmus paper in a base medium to give you a blue color. So you study the table and know which kind of indicator, when you place them in an acidic, alkaline, or neutral medium, what color change you get. So phenolphthalein in neutral medium, colorless, in an acidic medium, also colorless. But when you place phenolphthalein in a basic medium, you have red. The same thing when you place methyl orange in a neutral medium, it will give you the same color, that is orange, the same color as it is. But when you place the methyl orange in an acidic medium, you get either red or pink. Sometimes you see it as if it's reddish pink. Then methyl orange in a basic medium to give you a color change of yellow. So this table explains or gives you how these indicators, when they are used in various solutions, would give you a color change. So this table, you study the table and know the color change when you are given the slides. Don't just keep the slides at just keep them somewhere, but rather you would go over them and be reading to understand what they mean. To understand what they mean. So determination of pH of a solution. Now, how to determine the pH of a solution? How it's done? Now you add a few drops of indicators to the solution. You shake the solution to observe the color change that occurs. So if you have an acidic solution, when you add the indicator, then you shake. Now when you shake, you compare the color to when you started to know whether the color has changed. At the point where it has changed, then you compare the color to the chart and know whether the substance is a base, acid, or it's neutral. The pH of that solution, the pH of the solution is the pH of the color that it matches to. Okay. This would be, I was thinking the class wouldn't be too long, so I had to add what we'll be doing in our next lesson. Um, I'll just go over them in a bit so that you can ponder over what I just taught you. So in our next lesson, we're looking at forces, motion, and pressure. Forces, motion, and pressure. So we'll first deal with force. After we're done with the force, we'll go to motion, then we'll look at pressure. So you have a basic definition for the force as a pull or a push. When you pull something or you pull or push something, we say you are applying force. So at the point where you are sitting down, when you stand up, you've applied a force. When you sit down, you're applying the force. When you shake yourself, anything that you are doing, you apply a force for that to occur. Now, you can also define the force at that change in the body's state of rest or of uniform motion in a straight line. I'm applying the force. When I'm standing, I sit down, I'm applying a force. You stand up and you are walking about, you are applying a force to walk. When you are even nodding, you are applying a force to nod. So everything that we do, we normally apply force for it to occur. Now, force is measured in Newton. So the SI unit for force is Newton, capital N, or kilogram per meter square. So you have the SI unit there, kilogram per meter square. So either Newton or in an express form as kilogram per meter square. Now look at effects of force. What can force cause on us? One, it can cause a body at rest to move, as I already explained. It can also cause a body in motion. So when you are standing up, you can also stop. When you are moving, you can stop. It's also by force. Causes a change in direction of moving objects. Force can cause the change in direction of moving objects. It can cause or it can cause the change in speed of moving objects. It can also cause a change of the shape of objects or deformed objects. It can change or deform an object depending on how the force is being applied to the object. Then it decreases the speed of a moving object or a moving body. So when someone is in the car and wants to apply brakes, force is being applied for that to happen. So it decreases the speed of the person using the car. Now, mathematically, force can be defined as mass times acceleration due to gravity. So you have mass having the symbol of m, then acceleration having the symbol of a. So you have F, force is equal to mass into bracket m times acceleration a. So you have F is equal to ma in a simple form. Now next week I'll go over the same thing so that you understand. But I just want you to have a background so that you can solve the question for me that I've provided at the latter part of the slide. So F is equal to ma, that's m times a. So you have mass being measured in kilogram, then acceleration measured in meter per second squared. So when you multiply the two together, you have kilogram per meter per second square. Kilogram meter per second square, sorry. Kilogram meter per second square, or Newton. So these are work examples. So you have an object of mass 4 kilogram undergoes a uniform acceleration of 25 meter per